Hey, Charlie, listen to this. A vector is a quantity that has two parts, magnitude and direction, and it's usually shown as an arrow or directed line segment. The arrow points in the vector's direction, and its length is proportional to the vector's magnitude.
Yeah, if it's drawn a scale.
That's right. There are two ways of naming vectors. Calling the whole vector by one letter, like A.
Well, you mean small a, don't you?
Yeah, or you can name it by its initial and terminal points, like capital AB.
Chase 1, do you copy?
Oh, yeah, Chief, we copy. Go ahead.
There's a disturbance at Bob's Lodge on Route 7.
On our way. Punch it up on the screen, Ed.
There it is. Well, it's going to take a while to get there. Unless...
Yeah, that's right. Unless we use vectors. Plot the vectors, Ed, and give me the resultant.
Got it. Head northeast and floor it.
Oh, no, not again. Great vector, Ed.
Sorry, Charlie.
Not all problems can be blamed on vectors. When two vectors are joined, the resultant is found by drawing a line from the initial point of the first vector to the terminal point of the second vector. In this case, the resultant vector AC is the sum of vectors AB and BC. If the magnitudes of two vectors are the same, and they also have the same direction, then the two vectors are equal. As long as the magnitude and direction of a vector are kept the same, it can be moved to any location. Here are two vectors. A is 4 units east, and B is 3 units north. A and B must be joined before their resultant can be drawn. Keeping the magnitude and direction of vector B the same, it's moved so that it touches A. The resultant can now be shown. As it happens, this forms a right-angled triangle with two known sides. Triangles which have a right angle are among a special set of triangles which have some unique properties. The Egyptians used right-angled triangles 4,000 years ago for construction and surveying. 2,000 years ago, the Greek philosopher Pythagoras became fascinated with the right-angled triangle and developed what is now known as the Pythagorean theorem. The theorem states that in a right-angled triangle, the square on the hypotenuse is equal to the sum of the squares on the other two sides. Returning to the example, the magnitude of R can be found by using the theorem. Square the magnitudes of vectors A and B, add them together, and find the square root of the total. So the resultant's magnitude is 5 units. This triangle is particularly unique in that with the two sides forming the right angle being 3 and 4, the length of the resultant is another whole number. All that remains now is to find the direction of the resultant R. To do this, we need to use the relationships found in trigonometry and think of A, B, and R as simply the sides of a triangle. First, we'll call this angle theta. Next, the sides are labeled. The longest side is labeled hypotenuse. The side opposite angle theta is labeled opposite, and the remaining side, the one adjacent to angle theta, is labeled adjacent. Now we need to find the tangent of angle theta, or tan theta. Tan theta equals the ratio of the length of the opposite side to the length of the adjacent side. (3 over 4, or 0.75. With a calculator, we find that theta, the angle itself, is 36.9 degrees. If we now replace the trigonometric notation with the original vector names, we see that the direction of the resultant r is 36.9 degrees north of east, and its magnitude is 5 units. Although what we've just done appears to be only an exercise, there are times when knowing the direction of a resultant is most important. An airplane is flying due west at 240 kilometers per hour in dense cloud cover. The wind is to the south at 70 kilometers per hour. The pilot needs to know how the wind will affect his plane's speed and direction. If the wind's vector is redrawn from the terminal point of the airplane's vector, this then is the resultant vector r, and is the true course the airplane is following. Using the Pythagorean theorem, we find the magnitude of r is 250 kilometers per hour. The pilot's instruments tell him that he's flying at 240 kilometers per hour. But the magnitude of vector r, which takes the wind's effect into account, tells us that the true ground speed of the airplane is 250 kilometers per hour. Now we need to calculate the angle that represents how much the plane has been blown off course. Let's call this angle alpha. And find its tangent. Tan alpha equals the ratio of the length of the opposite side to the length of the adjacent side. Or 70 over 240. With a calculator, angle alpha is found to be 16.3 degrees. So, the true ground speed of the airplane is 250 kilometers per hour, and its course is 16.3 degrees south of west.
I'm not so sure this was a good idea. What's our vector, Ed?
Well, according to my calculations, the resultant points straight down. Oh, no. Start swimming, Charlie. You know, we keep ending up in the water. Or maybe we should join the Navy.